This is Ms. Brigham with today's video in section 2.3, the derivative function. As you're watching the video, please take down any important notes, formulas, equations, or statements, feeling free to pause the video as needed. At the end of the video, please write down your summary and then submit the summary online as well as your top question. Let's begin. So we've been talking about the derivative so far in the last few videos, and today we're going to look at 3 ways to determine the derivative function. So we're going to estimate the derivative graphically. A little bit later on, we're going to estimate the derivative numerically. And then lastly, we're going to determine a formula for the derivative. So if you recall, the derivative at is the slope of the tangent line at the point. So if I have a function, to determine the derivative is to draw tangent lines at various points and then calculate the slope of these tangent lines. You'll notice a few things, and one of the few is that for each x value of this graph, there will be at most one slope of the tangent line value. That seems to be like something we in algebra, which is whenever you have the case that for each x input there is at most one derivative or output, which in this case is the derivative value at that point, then it seems like that the derivative is also a function based off of x. To define this function, the derivative, if we have an original function f, we define the derivative function f prime to be a function based off x, where each output value is the rate of change of f at x. And we can also describe it using this limit definition of this difference quotient, which ends up being the slope of the tangent line as we once the limit of h goes to 0. So now we have a way to define the derivative function. And so now let's take a look back at our original problem and see if we can graph this derivative function. Well, since we're talking about estimating the derivative graphically, I want you to know that values of the derivative function give you tangent and slope values of the graph. So all I need to do is find the slope of the tangent lines, and I will have my points, and I can draw a line connecting these points. So if I were to calculate the slope of the tangent line here and here, I would notice that it's positive, and here it's positive. And then notice that the slope of the tangent lines are negative at 0, 1, 2, and 3. So it seems like my graph will have my derivative graph will have positive output values between -2 and about 0.5, and it will have negative output values, the derivative function, between -0.5 and about 3.5, and then it'll have back to positive values from 3.5 till about 5. So let's see what that would look like once we were to graph it. And as you can see, if this is our derivative function here, that is positive as we go from -2 to -1, about -0.5, and then it becomes negative from -0.5 to about 3.5, and then it becomes positive as we go from 3.5 on. So it seems to me that we have a derivative function that is consistent with the slope of the tangent lines that we saw over here to the left. Another thing I want to point out is that if f prime is positive on an interval, as we saw here from -2 to 1, to -0.5, and from 3.5 to 5, then that means that f is increasing. The original function is increasing over that interval. And that when the derivative is negative on an interval, as we saw from -0.5 to 3.5, then that must mean that the original function is decreasing over that interval, and this is the case. So not only does the derivative function give us the slope of the tangent lines, it also lets us know about the original function on the interval, whether it's increasing or decreasing. Great. Now let's take a look at estimating the derivative numerically. So I have a problem from example 3, which talks about the concentration of drug in a bloodstream over time. And they want us to construct a table of estimated values for C prime of t, which would be the derivative of the concentration function with respect to time. So if we take a look here, here is our original concentration values, and as you can see, the concentration values are increasing over a set time interval of about 0.1 minutes. 0, 0.1, 2, 0.2, 0.3, 0.4, all the way up to 1.0. So the change in time is about 0.1 minutes. So if we take a look over here at our concentration values and look to see how they're changing, we see that the change is increasing here, 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 and then it stops, and then it starts decreasing here, here, here. So if we were to take a look at our calculating the slope at the average rate of change over these intervals, which would be the way we would estimate the tangent, the slope of the tangent line at these points, we would see that the tangent line would seem to be increasing from 0 when x is from 0 to 0.4 minutes and decreasing when x is from 0.5 minutes, sorry, not x, but time, to 1 minute. And what's very interesting going on over here is it seems like that there's no increase because the concentration values are the same. So the slope at this tangent line here would be about 0 because there is no increase. Whereas the slope of the tangent lines are positive to the left of it and negative to the right of it. So we can use this information to actually compute the average rate of change over the 0.1 interval, which is what we've done here, and we're going to include that as our derivative function of c, because these are the slope values, again positive as we can see, between 0 and 0.4, and then it's negative between 0.5 and 0.9. So when we plot these values on a graph, if this is our original graph, the plot of these values are going to look something like this. So I plotted these xy coordinates of the derivative function, and as we can see, it's going to end up looking something, the graph is, if I were to draw a line between them, with something like this. Sorry. Sorry, I can't draw. Okay, all right, so that's the one way that you could estimate the derivative numerically, is by basically taking the average rate of change over the intervals and determining those values, and those values would correspond to an estimation of the derivative of the derivative of the function. Okay, last but not least, we're going to talk about the derivative function from a formula, and you're going to be responsible for memorizing a lot of these formulas. So I suggest you start making a list. And some of them are kind of self-intuitive if you were to think about it. So let's take a look at one of the simplest functions out there, which is the constant function. It's a horizontal line at some value, f of x is equal to k. But what you should know is that the slope of the constant function is 0 because the y values are not changing at all, even though the x values change. So that would mean that the derivative at each of these points would be 0 because the tangent lines will have a 0 slope. So since the tangent lines have a 0 slope, then the derivative of any constant function is going to be the 0 function, which means 0 at each point. If we take a look at a linear function where the slope is constant, then the slope of the tangent line at each of the points is going to be the same value, since a linear function has constant slope. So it just means that the derivative function will be the same as the slope value. That won't change as well because it doesn't change, the slope doesn't change for a linear function, so the slope of the tangent line won't change for the derivative function. So the slope of the tangent line will be equal to the same slope of the original linear function. And that means we have another constant function, but instead of being at 0 for the derivative of a constant function, it's at m. And last but not least, we talked about this last class, the derivative of a power function. We kind of derived it in the activity that if f of x is equal to x to the n, then the derivative of the power function is n times x to the n minus 1. We'll have plenty more to talk about in the upcoming days, but these are ones you should know like the back of your hand. All right, thank you.